be a classic hydraulics problem. Um, First thing I always like to do when I'm going over FEP problem, and in this case we're talking about PE today, is just looking at this exam specification. So this is all available on the NCEES website. And once you log in, make an account, you'll have access to these exam specs as well as the PE reference manual, which will be your bread and butter for the exam, computer-based testing at this point. Um, so right here, we're looking at hydraulics and hydrology, and A is talking about open channel flow. So that's a problem we'll be working on today. All right. So what do they mean by open channel? Let's just talk about that first. So open channel means you have one surface um, that is free to atmosphere. So in this case, you can see we have three sides um, that the water is actually touching on what we can call a concrete structure for simplicity. And we have one side that is exposed to atmosphere, indicated with this triangle at the top. All right. So this is the level of atmosphere above. So all this white space, blue is water. All right. So that's the basic setup for us. So what's the problem asking? That's to determine the velocity of water flowing in the channel, giving Manning's roughness coefficient of 0.05 and a channel slope of 1.5%. And to provide an answer in feet per second. So make sure you take advantage of reviewing your units. Do not use incorrect units or you will not get the desired output. All right. So let's go to the reference manual, see if we can determine a good equation to use. You'll want to get very familiar with this reference manual. I just got some bookmarks on my Bluebeam account. These bookmarks were already created with it, but I am using Bluebeam to access this PDF. All right, so 6.4, open channel flow. I'll keep scrolling down here until I see something related to Manning's equation, Manning's roughness coefficient. And here we go. 6.45, steady uniform flow. And we're looking for velocity, which is V, flow velocity provided in feet per second. The rest of the equation right here is 1.486 divided by N, which is Manning's roughness coefficient, multiplied by the hydraulic radius in feet. And the hydraulic radius is a function of the cross-sectional area of flow provided in feet squared, divided by the perimeter or wetted perimeter, P. And the wetted perimeter is going to be only the distances that are touching the water. So on your surface, you're not going to be including that length that is exposed to atmosphere. So wetted perimeter is it's pretty self-explanatory. All right, and then we have slope, which is a foot per foot. So we do have something that's given in percentage. We're going to have to convert that to a decimal for our equation. All right. Let's go back to our problem and start writing down the equation we're given. So V, oh, 2, V is equal to 1.486 times R 2/3 times S to 1/2. All right, and we know that N is equal to 0.05, and S, we're going to go ahead and convert that now, will be 1.5 over 100. Okay. Which is equal to 0.015. All right. So now we can go ahead and start plugging this stuff into our equation. But the first thing we need to do is determine our hydraulic radius. So again, hydraulic radius is equal to area over wetted perimeter. So what's the area? The area, if you don't realize, is a trapezoid. You can go ahead and calculate the trapezoid as a function of square and two triangles, but I'll just go ahead and use the area of a trapezoid If you are unfamiliar with area of a shape, good bet would be looking in the static section. 1.5.6 does give you some good equations related to statics, but it also gives you a chart that you'll be using throughout the exam. And this chart also just has basic areas that you can use. So in this case, the area of a trapezoid is provided. So this is the one I'm going to use. Area is equal to H times A plus B divided by 2. So we'll go ahead and put that over here for our problem. A is equal to H times A plus B divided by 2. In this case, the height is 4. Times A. A is going to be, we can use this length distance right here, so 5 feet plus B. So in order to determine B, we're going to need this entire distance right here, okay? This is B. And what will prevent us from having this distance is these two ends right here. So we know this 5, we don't know this, and we don't know this. So that's what we're going to have to find. All right. That's what this is. All right. So that's perfect. All right. So now you understand this is a triangle over here, a triangle over here, and we need to find this entire distance right here. All right. So let's think about this from a trigonometry standpoint. We know that this height right here is 4. So we can go ahead and use the tangent to find this side that's missing. And the combination of this will give us the B. So let's break this down over here below. All right. Well, actually over here to the left. So tangent of 45 is equal to, is equal to 4 divided by x. So in other words, if I wanted to solve for x, x is equal to tangent of 45 divided by 4. All right. Pretty self-explanatory right there. So we can go ahead and plug this in now. So we already have this other 5 for A, and now we're going to head and plug in what B is. So B is going to be plus 5, because we still got to include this length right here. And we have these two smaller sections, which we know are now tan of 45 divided by 4. Plus tan 45 over 4. We have 2 of these. All right. And all of this is over 2. All right. Recenter us a little bit. All right. So now just putting this in the calculator, you can go ahead and get a number. So I use the TI-36X Pro. That's one of the recommended calculators just because it doesn't have graphing function, but it still has everything else you'll need. It does compute formulas and things like that, so pretty handy calculator. 21. So our area is equal to 21, and now we need to determine our hydraulic wetted perimeter. So we got the area of flow, and now we need the wetted perimeter. So perimeter is just going to be 5, and we need to find these two ends right here too. So another trigonometry effort. So in this case, we can do sine to find out what this side is. So we'll call this x right now. Sine of 45 degrees is equal to 4 divided by x. All right. So x is equal to 4 divided by sine of 45. All right, so that's just opposite over hypotenuse. And that's going to give us 4 divided by sine of 45. That's giving us 4 root 2. All right. So now if we want to find out what the entire perimeter is, we know that this side is equal to 4 root 2. So we're going to have 4 root 2 plus 5 feet plus another 4 root 2 over here. So the wetted perimeter two times 4 root 2 plus 5, which is equal to percent. So not too bad. The main thing with this one is understanding what equation to use and knowing how to use it effectively, and understanding the wetted perimeter. So you're not taking too much of the perimeter. If you had included all 4 sides of the trapezoid, you would have given the wrong answer. Or for whatever reason, you were using the incorrect units. But in this case, all the units were given to you in feet. So pretty straightforward problem. Go through the process. I recommend that you switch up the numbers. Maybe give yourself different units, or instead of looking for velocity, you could go ahead and try to find the Manning's roughness coefficient given the velocity. So definitely try to mix these problems. I said meters per second. Obviously, it's supposed to be feet. Rookie mistakes. Be better than me. All right, I'm leaving for good this time, guys. Bye.